When they react, this is general information. It might be slightly advanced for your level, but I wouldn't worry about being restricted to the level that you're advised to follow. We're aiming at your IG level and we're aiming at your A level. So foundation is introducing topics, but the sooner that you grasp the basic concepts, the better. It's going to make you stronger chemists. Okay, so metals in general have got 1 to 3 electrons in the valence shell. Metals lose electrons to form positive ions. Non-metals accept electrons and will form negative ions. Metals possess low electronegativity. That means that metal atoms want to give away electrons in order to bond, while non-metals attract electrons. Having a high electronegativity means that they draw electrons towards them. Metals combine with oxygen to form metallic oxides. These metallic oxides are basic in nature, while non-metals generally form acidic oxides. If you think about sodium oxide, it's alkaline, while hydrogen, wrong example here. If we were to consider CO2, that's a non-metal formed with oxygen. Carbon dioxide dissolves in water to form the weak acid carbonic acid, H2CO3. Carbonic acid is why soda water has got that slightly sour flavor compared to still water. Metal plus water gives you metal oxide and hydrogen. Metal and acid gives you salt and hydrogen. So these are a couple of general equations. Non-metal and water, no reaction. Non-metals just don't react with water.
So today we are talking about the structure of the atom, and if we have time, we are going to talk about a little bit about isotopes, which is actually the week 1 in your course when you open in the Cambridge Learn site. Okay, so let us begin with this page, and this top part actually. I copied it straight from the video that appears in week 1 in the Cambridge Learn site, so that we are in the same wavelength and we work together with week 1 as it is in your course. So we see that it talks about the atom. The atom has a structure. What does this mean? It has a structure. It means it's made out of smaller particles. The atoms are not the smaller particles of matter. Today we know that they consist of a number of other smaller particles, which are called subatomic particles, and these particles are protons, neutrons, and electrons primarily. In the future, we are going to see that some of these particles have also consist of even smaller particles, but for now, we are going to be concerned with these 3 types of particles. So we are going to talk about the protons, the electrons, and the neutrons. Now, roughly, this picture that you see here, it's how we can represent very roughly an atom. This is not how an atom looks like, of course, but this is how we can show it with a drawing to show the main particles and where they are. So we see that there are some big particles shown here in red and green, which make up the nucleus of the atom. All this part here is the nucleus. It's called the nucleus. Let's write it here with bigger letters. Nucleus of the atom. Let me write it properly because it's terrible. All right, so this is the nucleus. nucleus of the atom, which is at the center of the atom. We imagine being at the center of the atom. And this nucleus, as we can see, consists of two types of particles. Here they're shown in red and green. The red is supposed to be protons. So the red ones are protons. I don't think you can see this little text here. Let's write it with bigger letters. Proton. These are protons. They have a cross here to show that these are positive particles, positively charged particles. And the particles that are shown in green here, these green particles, are the neutrons, are called neutrons because they are neutral, meaning that they don't have any charge. So these are the neutrons and the protons. The nucleus of the atom consists of these two types of particles, neutrons and protons. And a third type of particle that we meet in the atom, a very important particle, are the electrons. The electrons that we find them around, they orbit around the nucleus, in the space around the nucleus. And these are very tiny and small, but nevertheless, they are very, very important particles. Let's call them electrons. And the electrons have a negative charge. That is why we show them with a minus here, representing the negative charge. So the electrons have a negative charge, the protons have a positive charge. That is why they show them here with a plus, the protons, and the minus here, the electrons. And the important aspect of the electrons are that they are found outside the nucleus, and in the space around the nucleus, and they orbit the nucleus at the specific spaces. We are going to talk about that. So the main thing about the structure of the atom for the time being is that the nucleus of the atom is found at the center of the atom, and it's made out of protons and neutrons altogether. And around the nucleus, we find the electrons orbiting the nucleus, and we're going to talk a bit more about the electrons just now. So these are the three important subatomic particles that we need to know for the time being. Now, an important aspect now, before we change this page, is that different elements, now from the elements of the periodic table, different elements have different numbers of electrons and protons. And how many protons an element has kind of defines what element we are talking about. So as an example, here, these little pictures at the bottom, for example, we have three different atoms of three different elements. We have a hydrogen, and we see that the hydrogen is made out of one electron. It has one electron orbiting its nucleus, and the nucleus of the hydrogen most often has one proton. So this would be a hydrogen. It has one proton, one electron. The next one represents a helium, the helium element, an atom of the helium element. Now a helium atom consists of two protons and some neutrons and two electrons, two protons, two electrons. So we see, because you see different number of protons and electrons from the hydrogen. That is why it's a different element. This is a hydrogen, this is a helium. The next one is an atom of lithium. The lithium, as we can see, has 1, 2, 3 electrons and 3 protons. So that is why, because it has a different number of electrons and protons, it's a different element from the other two. Another aspect that we can notice here, very, very important aspect, is that in a neutral atom of any element, the number of protons equals the number of electrons. So the protons which are in the nucleus and the electrons that orbit around the nucleus are the same numbers. So that is a very important aspect of a neutral atom of any element. So here we see the hydrogen, for example, has 1 proton, it has 1 electron too. The helium has 2 protons, it has 2 electrons. The lithium has 3 protons and 3 electrons, and so on. And here I have another picture with many more different elements, atoms of different elements, to see again that the number of protons in the nucleus equals the number of electrons in a neutral atom. Be careful now, we're talking about neutral atoms, because in the future we're going to see that some atoms are not neutral if they have more or less electrons than what they should have. So, for example, here, I hope you can see it. Let's make it a little bit bigger. The hydrogen already, we saw that hydrogen has 1 electron and 1 proton. Carbon, for example, which is another very important element, carbon, it has 6 protons and therefore it has 6 electrons all around it. Nitrogen has 7 protons, 7 electrons, and so on. Oxygen has 8 protons, 8 electrons. And there's no need to go through all of them, but it's very, very important to know that the number of electrons and the number of protons in neutral atoms is the same. And now, how can we tell now how many protons and how many electrons are there in atoms? And we cannot remember everything, but in this, all this information now is summarized. Well, it's contained in this very important table, the periodic table of the elements. And this top table actually is the one that I found it from the Cambrian site. I think it's also from the video. They include this periodic table, so I have it here. And this periodic table somehow contains all the elements that we know. In reality, I can see that this, in the past few years, actually, we have discovered more elements. This is not the latest periodic table. Here below, actually, we have this periodic table, which I found on the internet, contains more elements, as you can see here. All these elements that are missing from this row are here. So anyway, up to now, in other words, up to now, 2020, these are the elements that we know of. Some of them, we make them in the lab. They don't exist in nature by themselves, naturally, but nevertheless, we can make them in the lab. So these are all the elements that we know up to now. And you can see that in the periodic table, every little square now corresponds to one element. And so every little square here, as you can see, you cannot see very clearly, but we can increase it and you can see it easier. Each little square that has information about is particular element, say for example here, boron. You see, it has certain numbers. Every square here has certain numbers. There's a 5 up there, and there's another 10,8, 811. There's another number down here. There are other numbers down there, up there, +3 it says. And similarly, the top periodic table, you see, has also some numbers. It has another number on top for boron, says 5. Compare this with the periodic table at the bottom. I wish they could fit in the same place, but nevertheless. And there is an 11 down here. And there's some other number there. So we see that each periodic table, depending on for which purpose we want to use it, has certain information for each element. And because different tables contain different information, every periodic table that we're going to find, including in our book, has a key here that tells us what those numbers represent. So we are going to be concerned here with just 2 of these numbers. The number which is shown here on top, in the case of boron, this number would be 5. And the number which is here at the bottom, in which case here it says 11. And if we look at the other periodic table again, this we see this number 5 again at the top left actually here. They tell us that this is the atomic number, this 5. Whatever number we find on the top left is the atomic number of this element, whose symbol is B, in this case it's the boron. And the bottom number represents the atomic mass of this element. The same thing applies to this periodic table. This number here represents the atomic mass. They tell us that the number that we see at the bottom is the atomic mass, and the number that we see at the top, up there, corresponds to the atomic number. So for boron, the atomic number is 5, and its atomic mass is 11, or close to 11. This is not a round number. It's 10, according to this table, it's 10,811, which means if we round it up, it's 11. That is why the top table shows an 11 down there. Okay. So these two numbers are the numbers that we are going to be concerned. The atomic number and the mass number. Remember, the top number is the atomic number, and the bottom number is the mass number. So those two numbers are very important for us. And let us look. Let us continue with our pages here. Yeah. So here I have the picture of an element from the periodic table, which is helium. And here we see the top number will be the atomic number. They tell us the atomic number. The number at the bottom, which is about 4, is the atomic mass, the mass number. The mass number. Okay. So why do these numbers are special, and what do they represent now? Now, the atomic number is actually, it shows how many protons this the atom of this element has. So the helium element, an atom of the helium element, has two protons in its nucleus, and of course, if it's we're talking about a neutral atom of helium, then it has also 2 electrons orbiting this nucleus. Now, what is the mass number? The mass number, with the word mass, means that this is all the mass of the atom. It's the mass number is actually shows how many protons and how many neutrons the nucleus of this atom has. So the mass number is actually the number of protons plus the number of neutrons that we find in the nucleus, because the number of protons and the neutrons actually make up the mass of an atom, because the protons and the neutrons are very big particles in comparison to the electrons. They're huge particles in comparison. The electrons are so small, tiny, that we can ignore them. We can ignore their mass. So the mass of an atom, for all practical purposes, is made up of the mass of the protons and the neutrons. So in other words, the mass of the mass of an atom, it's actually the mass of the nucleus, because in the nucleus is where we find all the protons and neutrons. So let us see in order here, what do we have here? The atomic number, which is usually at the top of the periodic table, in each box that corresponds to an element. The atomic number, which sometimes we give it the symbol Z, shows the number of protons only, the number of protons in the nucleus, and the number of electrons if we're talking about neutral atom. And why do we call it atomic number? Because this number, the number of protons, kind of defines which element we are talking about. We said that we saw earlier in the pictures that hydrogen, for example, has just one proton, and it's one proton is hydrogen, and hydrogen has always one proton in its nucleus. Carbon, another element, has always 6 protons. If we have an atom with 6 protons, we know that it's carbon. And if we know that we have a carbon atom, we know that it has 6 protons. It cannot be anything else. So because the number of protons, in other words, define which element this is, that is why this is called the atomic number. It's characteristic of the atom. Specifies which atom we're talking about. Nitrogen has always 7 protons. When we see 7 protons, an atom with 7 protons can only be nitrogen, nothing else. And that is why the number of protons is called the atomic number. Specifies which atom we're talking about. And of course, in a neutral atom, the number of electrons is exactly the same number as the protons. And the number of electrons in a neutral atom specify what will be the chemical properties of this element. Okay, so the atomic number determines what element we have. Okay, so the atomic number corresponds to just one particular element, and this particular element has always the same number of protons. Now the mass number we said is the number of particles in the nucleus, which are both the protons plus the neutrons, because these two types of particles give the mass of the atom. All the mass is actually concentrated really in the nucleus, because the mass of the electrons is so small, which is like negligible. In fact, look at this. The electrons weigh 1/2000 of a proton, of the mass of a proton or a neutron. So small they are. So it's so tiny that we ignore their mass. And so now we understand what is the atomic number that we see showing in the periodic table in each element, and of course the mass number, which are very two important numbers of each element. And of course this would be the symbol of helium, of this element helium. And it's a good idea to memorize the first few elements in the periodic table at least. Slowly you're going to learn by heart up to the element with atomic number 20, the first 20 elements. But take it easy. I mean, at the beginning, if you memorize the first 10, that would be great. Okay. So this is now these important numbers that we meet in the periodic table that are characteristic of the atoms of each element that we have in the periodic table. So now we spoke about electrons, that each atom has as many electrons as protons in the nucleus of a neutral atom. So here we have now, let us discuss now where do we find these electrons, because these electrons are not just randomly orbiting around the nucleus. They orbit in particular energy level. They have particular energies. For the time being, you just need to know that there are certain energy levels that we can find the electrons around the nucleus, and we represent these energy levels with circles, but be careful now, because these circles show, for example, the first circle that we draw shows that how many electrons we can have at this energy level, and by energy level we mean how much energy these first two electrons can have. The lowest energy that electrons can have, we represent it with this circle, and this circle, the first circle, the first from the nucleus that is, can only take up to 2 electrons, no more than 2 electrons. If this first energy level has 2 electrons, we say this energy level is complete, and if the atom has extra electrons, we put them in further energy levels, like in the case of lithium. Look at this. An atom of lithium has 3 electrons and 3 protons, of course, in its nucleus. Where do we find lithium in the periodic table? Here it is, and the hydrogen. Lithium. You see here, this 3 up there shows the atomic number of lithium, which means that it has 3 protons, and of course 3 electrons if it's a neutral atom. So 3 electrons. The first 2 electrons go into the first energy level, which we show with a circle here. And but the third electron cannot go there anymore. It has to go to the next energy level, which is the second energy level. So here we see here, this is energy level number 1, and this is energy level number 2, the second circle. So the third electron has to go to the next energy level, which is number 3. And it doesn't matter. This is just a representation of roughly where we can place the electrons to show the different energy levels. Now, whether you place it the third electron there, or you place it there or there, it doesn't matter. As long as you show 2 electrons in the first energy level and 1 electron in the second energy level. We can also represent the electrons instead of drawing little circles. We can also represent them with an X. It doesn't matter as long as you show where we place the electrons, which energy level. So this is 3 ways to represent lithium atom from different sources. You can see different people draw an atom of lithium a little bit differently, but we need to make sure that we understand how the electrons are represented and what these circles here mean. They just mean energy levels, mean how much energy these electrons can have. For example, we can see another example, which is not helium, but not lithium, but something else. Like this is a sodium atom, for example. Sodium. Let's see, where is sodium in the periodic table? Here it is. You see where it is, and it has an atomic number 11, which means the sodium has 11 protons, and of course 11 electrons in a neutral atom. So we have to place 11 electrons all around the nucleus. So the first 2 electrons, remember, the first 2 go to the first energy level that can only take 2 electrons, okay, only 2 electrons. The second energy level can take up to 8 electrons. The third energy level can take again up to 8 electrons, and we're not going to see any bigger atoms for now. So this is what we need to know for now, because after that it becomes a bit more complex. But for now, we just need to know about where to place the electrons of the first lighter elements. So here we have the sodium. Remember, sodium has 11 electrons, and of course 11 protons in its nucleus. So 11. The first 2 electrons go to the first energy level that can take only 2 electrons, 1, 2. Then the next electrons, we have to place them in the second energy level that can take up to 8 electrons. So we have 2 already. Another 2, 3, 4, 5, 6, 7, 8, 9, 10. So you see the second energy level can take only 8 electrons. So up to now we have completed the second energy level, but we still have 1 more electron left because sodium has 11 electrons. So up to the second energy level, we have placed the 10. So the 11 has to go to the next energy level, and there it is all by itself because we have finished placing the electrons of the sodium. And we say now this type of diagram, we can call it the electron configuration of the sodium atom, because we have configured where its electrons go, in which energy levels. And the same with if we had magnesium. A magnesium atom has 12 electrons. And if we look at magnesium, if we find magnesium in the periodic table, you see it's next to sodium. It has 12 protons. And which means the first 2 go to we place them in the first energy level, then another 8 to the second energy level, like sodium. And the last 2, the remaining 2, have to go to the third energy level. And here is the electronic configuration of magnesium. So you see this one with 11 electrons is sodium, but this one with 12 electrons, this is magnesium. It's a different element. Because we said different number of protons and electrons represent different elements, very different elements. And I think we can stop here. So next week we can continue with the isotopes, and perhaps if you want, we can make some more of these electronic configurations, but now I think we need to stop.